Hey everyone, how are you? In this video, I will discuss the concept of degrees of freedom in the context of data science project and its relationship to the course of dimensionality. So, degrees of freedom refers to the number of independent parameters or variables in a model or system. It represents the flexibility of the model to adapt to the data. In the context of statistical modeling, DOF or degrees of freedom is often used to assess the complexity of a model, with more complex models having higher DOF. Now, I will try to give an intuitive interpretation of degrees of freedom in the context of data science. So, the number of degrees of freedom you have describes your uncertainty in the data. If I am given two people's names, for example, Mr. A and Mr. B, and asked their ages, I know neither. So, in this case, I have 2 degrees of freedom, one for each person's age. If I am then told that Mr. X's age is 20, then I still do not know the age of Mr. Y, and in this case 1 degree of freedom is removed but 1 is still left. And then I am told that the mean ages, that is the average ages of both of them, is 30. This constraint removes the last degree of freedom, and now I know that Mr. Y must be 40 years old. So each time you find out or set something about the system you are working with, such as a value or a parameter, such as the mean average illustrated here, this decreases the number of degrees of freedom by 1. So degrees of freedom is a fundamental concept in statistics and data science that represents the number of independent pieces of information available in a sample for estimating certain parameters or making statistical inferences. In other words, degrees of freedom can be seen as the number of free choices that can be made in a calculation without violating any constraints or conditions. Now, further on the understanding of degrees of freedom with the example of a vector, because in data science and machine learning, we all know about vector very well. So if I have a vector of length 10, that can take any values, then I need all the 10 coordinates to know about the vector, and so that means in this case there are 10 degrees of freedom. Now if I am told that the sum of the elements of the vector is 0, then any 9 of the coordinates determines the 10th, and so in this case now I have the number of degrees of freedom which is 9. So the key idea here is that the degrees of freedom is a minimum number of values that you need to specify a quantity. If you are comfortable with geometry in the abstract, you can think of the degrees of freedom as the dimension of the space that the numbers live in. Now let's consider some example to illustrate the concept of degrees of freedom in different contexts. First example is room temperature. Imagine you have a room with 4 heaters and you can control the temperature of each heater individually. You are asked to maintain the average temperature in the room at 80 degrees Fahrenheit. In this case, you have the freedom to choose the temperature of the first 3 heaters independently. However, the temperature of the 4th heater is constrained by the condition of maintaining the average room temperature of 80 degrees Fahrenheit. Suppose you set the temperature of the first 3 heaters as heater 1 85 degree, heater 2 70 degree, and heater 3 90 degree. So the average temperature of these 3 heaters will become 81.67 degree Fahrenheit. To maintain the average room temperature of 80 degree Fahrenheit for all the 4 heaters, the temperature of the 4th heater now must be given by the following calculation, that heater 4 is 80 minus 81.67 minus 80, which will become 78.33 degree Fahrenheit. In this example, you have 3 degrees of freedom, as there were 3 independent choices, that is the temperature of the first 3 heaters, while the 4th heater's temperature is constrained by the condition of maintaining an average room temperature of 80 degree Fahrenheit. And the next example I will take is that of linear regression. So in the context of linear regression, degrees of freedom help us understand how much information is available for estimating the model parameters, that is the coefficients and the intercept, and quantifying the uncertainty around these estimates. For a simple linear regression with one independent variable x and one dependent variable y, we estimate two parameters, that is the slope and the intercept. In this case, the degrees of freedom are calculated as df, that is the degrees of freedom, is equal to n minus p, where n is the number of observations in the dataset and p is the number of estimated parameters, including intercept. Example, if we have a dataset with 20 observations and we are fitting a simple linear regression model with one independent variable and an intercept, the degrees of freedom would be 20 minus 1 plus 1, that is 18. The 18 degrees of freedom represent the amount of free information available for estimating the model parameters and characterizing the uncertainty around these estimates. And the next example is that of a t-test in statistics. So when comparing the means of two samples using a t-test, degrees of freedom play a very crucial role in determining the appropriate t-distribution to use for hypothesis testing. For an independent two-sample test, the degrees of freedom are calculated as df equal to n1 plus n2 minus 2, where n1 and n2 are the sample sizes of the two groups being compared. So suppose we want to compare the means of two groups, group A with 15 observations and group B with 20 observations. In this case, the degrees of freedom for the t-test would be 15 plus 20 minus 2 equal to 33. The degrees of freedom inform the t-distribution that we will use to conduct the t-test and draw conclusions about the statistical significance of the difference in means between the two groups. So in summary, degrees of freedom is a fundamental concept in data science that helps to understand the amount of independent information available for estimating parameters or making statistical inference. It is essential very much for characterizing the uncertainty around these estimates and informing the appropriate statistical distribution used in hypothesis testing. So you will often hear a statistician and data scientist say that do not add more variables because you will not have enough degrees of freedom. Let's understand this statement using multiple linear regression as an example. So in multiple linear regression, adding more independent variables reduces the degrees of freedom. The more variables you have, the higher the amount of variance you can explain. Even if each variables doesn't explain much, adding a large number of variables can result in very high values for your R-squared value. And this is why some packages provides adjusted R-square, which allows you to compare regressions with different numbers of variables. And the same holds true for polynomial regressions. If you have n data points, then you can fit the points exactly with a polynomial of degree 9 minus 1. So the degrees of freedom in a multiple regression equals n minus k minus 1, where k is the number of variables or the number of parameters you are estimating, and the additional minus 1 in the formula is for the intercept. It's an additional predictor, so the residual vector will exist in an n minus k minus 1 dimensional linear space, and that's your degrees of freedom in a polynomial regression situation. However, in simple linear regression, you estimate both a y-intercept and a slope. So k is equal to 2. Even though we generally don't worry about testing the intercept, it still uses up a degree of freedom. The slope would be very different and have a very different interpretation if we did not estimate an intercept along with the slope. So in this context of multiple linear regression, the more variables you add, the more you erode the ability to test your model. That is, the statistical power goes down of your model. Because as we add more variables, that is a parameter, the degrees of freedom decreases, leading to a higher variance of the parameter estimates and consequently wider confidence intervals for those estimates. This may result in less precise conclusions about the relationships between the independent and dependent variables. And this phenomena is closely related to the curse of dimensionality, where adding more variables or more parameters equates to adding more dimension. So you might wonder, why is it a curse? Well, the problem is that if we add more parameter to a multiple linear regression, but our input data remains the same, it will make it sparse at higher dimension. Let's look at this image below here, which will illustrate how the same number of data points looks very dense in a two-dimensional space, but looks very sparse in a three-dimensional space. Now imagine the sparsity in even higher dimension, maybe 4, 5, 10 dimensions. So we need more data to fill up the space, but often the data at hand is limited. So adding more variables while keeping the input data constant will result in loss of degrees of freedom and highly inflated R-squared values. Now let's talk about the curse of dimensionality. As the number of dimensions or features in a dataset increases, the complexity of the problem grows exponentially, making it more difficult to gain insights or build accurate model. Some issues related to the curse of dimensionality includes sparse sampling. As the number of dimension increases, the amount of data needed to cover the sparse grows exponentially. This results in sparse sampling, where data points become increasingly distant from each other, making it challenging to identify meaningful patterns or relationships. And the next issue with the curse of dimensionality is increased computational complexity, obviously, because high dimensional data requires more computational resources and time to process, which can be prohibitive, particularly for algorithms with a high time complexity, like for example SVM. Then the next issue is overfitting. In high dimensional space, models can become overly complex, capturing noise rather than the underlying data structure, leading to poor generalization of the new data. So overfitting can be explained through the bias variance trade-off, as we know. So as we add more variables to a model, we reduce its bias, that is a systematic error in the model's predictions, but increase its variance, that is the sensitivity of the model to small fluctuations in the data. And then another issue with the curse of dimensionality is model interpretability. Adding more variables to a model can decrease its interpretability, as it becomes more challenging to disentangle the effects of individual variables on the response. So overall, the curse of dimensionality and degrees of freedom are closely related, as high-dimensional data increases the complexity of the models, making them more prone to overfitting and also the other issues that we just discussed. But there is some solution, of course. So to address the issues of high dimensionality, you can do dimensionality reduction techniques, feature selection, and apply the regularization technique on your data.